Good evening everyone, my name is Renu Raman Sahu and today we'll be discussing about the physics of materials. Today is the ninth session and we'll be talking about the reciprocal spaces. So in the last few classes, what we did was we talked about the crystal structure. Why particularly the so we saw the importance to understand the crystal structure. Why? Because we set out with understanding the properties of particularly the metals, like why it is a very good conductor of electricity and why it is a very good thermal conductor. Then we saw that this free electrons, they cannot they cannot explain why the properties of material should be different in different directions. Like we talked about a material called graphene. So graphene was like very good conductor along a plane and not on the perpendicular direction. So there is a directionality to the properties of this material, and so that directionality is known as anisotropy. So since the experimental values like the conductivity, the refractive index, these are anisotropic, so what is it? What is it that is causing this anisotropy? And the answer is that it is the inherent underlying ionic structure which is giving this anisotropy to the material. So the electrons are basically seeing that ionic cores which constitute the crystals. Okay, we also saw that the energy is given by this h bar square k square over 2m. So what is this h bar k? The momentum, it is given by h bar k, and k is 2 pi by lambda, but lambda is it is nothing but de Broglie wavelength of the material. So in the real space, what we have is a crystal structure. Crystal structure is nothing but the periodic arrangement of the atoms or the ionic cores, and the crystal will have some direction or axis. So for example, there would be certain planes of the crystal, certain planes which have a particular direction. It will be the crystalline plane will be perpendicular to certain axis. So so these are the things which we can define in the real space. Today we will be talking about something called the reciprocal space, which will give more interactions. So this reciprocal space is what? This reciprocal space is related to the real space, in such a way that so it is just a kind of an equivalent notation, an equivalent representation, but it gives a more elegant information on the interaction of the waves which is interacting with it. For example, if you hit X-ray, how it will interact with the matter. And then we'll go on to, first we'll understand this reciprocal space, what it is, and then we'll see the evolved sphere, so which is a particular subset of this reciprocal space, and we'll see how these things will tell us more about the interactions of matter. So let us say that a crystal, so what is a crystal? A crystal, it is a periodic arrangement of the lattice points. So since it is a periodic arrangement of the lattice points, it can be yeah, I'm audible, right? Hello. Hello. Are you able to hear me?
Yes, sir. Actually, sorry, I went for taking a laptop.
Okay, no problem. Yeah. So, yeah. So, what is a crystal? A crystal is nothing but it is a translation of. So, a crystal is formed by the translation of this unit vectors or linear combination of this a1, a2, and a3. Okay, and corresponding to this unit vectors, so a crystal structure, how we can represent? Suppose a particular lattice point of that crystal, it is represented by a p a1 plus q a2 plus r a3, where this p q r has to be integers. P q r are integers. So when this p q r are the integers, then the set of all these points are that will constitute a crystal. So corresponding to this, we define a reciprocal space where the reciprocal lattice vectors are defined by this. So we just take this definition, we just take this definition as granted for now, and then we'll see what are the consequences of this. So the way we define, so we define three lattice reciprocal lattice vectors b1, b2 and b3 as. So when we talk about b1, it is a2 cross a3 divided by a volume v. We'll see what this volume v is. So when we talk about b2, we'll do the cross product a3 cross a1. So the way to remember this is a1, a2, a3. You think of it as a cycle, a1, a2, a3. So think of it as a cycle like this. So when you talk about b1, you have to do the cross product a2 cross a3 along this circle. So when you talk about b2, you have to do a3 cross a1 along this circle. And when you talk about b3, you have to do a1 cross a2 along this circle. You are getting, so this is the way to remember. Okay, so this is how you remember it. So now let us see what this physically signifies. So here is a triclinic cell. So what I mean by triclinic is a1, the magnitude of this a1 need not be equal to a2, need not be equal to a3, and the angles between them, so angle between a1 and a2, angle between a2 and a3, and angle between a3 and a1, they need not be same, or they need not be perpendicular to each other. So when we do the cross product a1 cross a2, what it is, a1 cross a2 is the area of the parallelogram spanned by a1 and a2. What it means is, like, if you have a1 here and a2 here, a1 and a2 here, then this area of this parallelogram, the magnitude of this is a1 cross a2, and a1 cross a2 is perpendicular. If you look at the what is the direction of a1 cross a2, it is perpendicular to this plane spanned by a1 and a2, so it is perpendicular. So the direction of this quantity a1 cross a2 is perpendicular to both a1 and a2, and its magnitude is same as the area spanned by a1 and a2. Now when you do this a1 cross a2 dot a3, so let us see what this is. So we have this here a1 cross a2. If you see this, a1 cross a2 is nothing but the area of the parallelogram spanned by a1 and a2. So this a1 and a2, a1 is what, OA, and a2 is OB, and the area spanned by that is OACB. Now if you want to find what is the volume of this parallelepiped which is spanned by a1, a2 and a3, then what you have to do, all you have to do is area of one of that parallel face, like let's say OACB, and what is the height of the next parallel face, what is the shortest distance between them, that you have to multiply. So if you take this, if you look at this a3 vector, the one shown in this black, this is a3 vector. So this is a bit slant. If you take the 90-degree projection OD, that is your height or the projection of a3 on the line which is perpendicular to this plane OACB, or OD is the component of a3 along the direction which is perpendicular to both a1 and a2, or you can think of it as projection of a3 on a1 cross a2. So the volume of this parallelepiped is nothing but this area of OACB, this parallelogram, times what is the height. The height is nothing but OD. OD is this length. So what is B3? B3 is this A1 cross A2 divided by volume V. So what is V? Let us see what is this. So if you try to take the magnitude of that, when you do the magnitude of that, you have to take magnitude of this as well. So magnitude of A1 cross A2 is nothing but the area OACB, and the volume is nothing but from this expression, it is area of OACB into height, and height is nothing but OD. So you just put this in place of this volume and you get this expression. This area of OACB that cancels, and what you have is 1 by OD. Now if you look, what is this 1 by OD is? So OD is a distance. So this distance we will denote as 1 by D001. 001 means this is 1 unit. So this D001 denotes the height between the distance between the plane, the distance between these two planes, the planes OACB and the next plane which is just on top of it. Okay, and since it is along the B3, so it has some non-zero component along B3, so that is why we will say it is like 001. If there is some non-zero component along, let's say B1, we'll say it D100, and if it is B2, then we'll say D010. So this in crystallographic notations, these corresponds to the shortest distance between the planes corresponding to a particular direction. Okay, so this is what we have about the this is how we have some intuition about this, what is this B1, B2 and B3 in reciprocal space. And note that it has this B1, B2 and B3, they have a length dimension of 1 by L. So this is the dimension, or L inverse. Now let us try to look some other properties. If you take the dot product of B3, if you take the dot product, let's say B3 dot A2, what is B3? B3 is A1 cross A2 by volume dot A2. Now see, this A1 cross A2 is perpendicular to both A1 and A2. That is why that dot product has to be 0. Similarly, if you take the dot product with A1, now this B3 is nothing but A1 cross A2, and it is perpendicular to both A1 and A2. So when you take the dot product, it has to be 0. But now if you have this thing B3 dot A3, which is, so B3 is 1 by V A1 cross A2, and A3 is this just A3, and we had this expression as, so what is this thing? So this dot product is nothing but so the magnitude of this was what? The magnitude of this is 1 by OD, and what we have is the projection of A3 on B3 is this dot product, and that projection of A3 on B3 is nothing but again OD. If you remember the previous picture, so that was just OD, and if you take so on the numerator also you have OD, and in the denominator you have OD. So just to give you a recap, so what is this OD? Is this is the projection of A3 on A2 A2 cross A1. Okay, or that like I hope that part is clear. So what will be happening now is, so whenever you see these indices like 3, 2, these are different, and see on the left hand side what we have is the reciprocal vectors, and on the right hand side we have the real space vectors, the unit vectors. B3 dot A2, so 3 and 2 are not same, so it is giving 0. 3 and 1 not same, it is 0. But when it is B3 dot A3, what we are getting is 1. Similarly, for other reciprocal vectors and this real vectors, what we have is, if we take this, for example, So what we have here is, if we take bi and aj and take the dot product, what we will have is this biaj. It will bi dot aj, its dot product will give me delta ij. Delta ij is nothing but, if I and j, these two indices are, if they are same, then it will give me 1, and if they are not same, it will be 0. So these are about the properties of the unit vectors in the real space and unit vectors in the reciprocal space. So what we have learnt is, we learnt about we learnt how do we get the reciprocal lattice vectors from the real space vectors, real space unit vectors. So given a crystal structure, we will have a real space unit vectors. From those unit vectors, we can get the reciprocal space unit vectors by this formula. By the formula, this v1 is equal to a2 cross a3 divided by v. So this is the formula for reciprocal unit vectors. Now once we have those unit vectors, we can find what is the relation between that reciprocal unit vectors and the real space unit vectors. And we found out that the relation is just this. The relation is this, just this. Now once we have this relation, now we can talk about, so now what we have? We have the unit vectors of a space called reciprocal lattice space. So once we have the unit vectors, now we can define any other vector in terms of those unit vectors. So let us say that, let us have a vector h of hkl, and it is defined as a linear combination of these unit vectors b1, b2 and b3. So it is h b1 plus k b2 plus l b3. Okay, so this is a vector sitting in the reciprocal space, a vector sitting in reciprocal space. Now let us see what we can, so what all information we can have about this. So this hkl, so this is the first information we get once we define this hkl as hb1 plus kb2 plus lb3. The first information what we have is, this h of hkl is perpendicular to the plane with Miller indices hkl. Okay, so this is the first information that we are we'll see. So we are going to see the validity of this statement. And the second statement that we want to infer is this, that the magnitude of this h of hkl is 1 by d hkl. So there will be a family of planes, and the distance between those planes is given by this d hkl. And if you take the, and d hkl is the shortest the distance between the consecutive planes. And if you take the reciprocal of that distance, that shortest distance between the consecutive planes, you will be ending up with this h of hkl, the magnitude of that. So now let us see what this plane denoted by hkl means. So a plane, so what is an hkl plane? An hkl plane is nothing but, so you have in real space, suppose in real space, in real space you will have some unit vectors. Let's say this is a1, this is a2, and this is a3. Now you define a plane which cuts this a1. So how do you know this a1, a2, a3? Given a crystal structure, you have this a1, a2 and a3. Now you define a vector, so you want to find what is hkl plane. So hkl plane is a plane that intercepts a1 vector at a1 divided by h, and it intercepts A2 at A2 divided by K, and it intercepts A3 at A3 divided by L. So this is the definition of the plane HKL. Sorry. So I hope you get this point what it is. So when we say, so the plane, so this plane is the HKL plane. So given a vector HKL, we are saying that corresponding to this there is a plane called the Miller plane, and it is defined by a plane which intercepts the unit vectors at a1 by h, a2 by k, and a3 by l. Okay, now our claim is that this h of HKL is perpendicular to this plane. Okay, that is perpendicular to the plane, and if there are more planes, so for example, if there are more such planes, let me just draw here as an example. So this and this, this, and there can be further more planes on, like you can imagine this stack of planes, right? So the distance between these planes, that is given by, so the distance between these planes d of HKL. So these are the HKL planes, and the distance between these planes is d HKL, and we are going to show that h of HKL, it has a magnitude of 1 by d HKL. Okay, so these are the claim, and h of HKL is perpendicular to this plane. This is perpendicular to h of HKL. Okay, I hope these 2 points are clear. Okay, so, and that turns out as a consequence of the fact that we have defined the reciprocal lattice vectors in that way. Now let us look at the validity of that statement. So here is the diagram. Here is the diagram that we have. Yeah. So if you look at this diagram, so this A, B, C, they constitute a Miller plane HKL. Why? Because this plane intercepts this A vector at A1 by H, B vector at A2 by K, and C vector, this A3 vector at A3 by L. Now if you look at the vector notation, OA plus AB will be your OB. So this is just triangular law of addition. Now OA plus AB is equal to OB. We know what is OA and what is OB. So OA is A1 by H and OB is A2 by K. So we just replace OA as A1 by H plus AB vector, and OB is A2 by K. Now we keep this AB on one side and take this A1 by H to the right hand side. So what we have is AB vector is equal to A2 by K minus A1 by K. Now let us look at what is this HKL. HKL we have defined as, this is H of H into B1 plus K into B2 plus L into B3. Okay, and if you take a dot product of HKL, H of HKL and AB, what you end up with is, so you're taking a dot product. Dot product is this, h of hkl is this, hb1 plus kb2 plus lb3, and ab is from this expression, ab is a2 by k minus a1 by h. Now if you take the dot product of these two, you see b1 dot a2, it will give 0. So if you expand this, what you have, you will have 6 terms total. So h by k b1 dot a2, k by k b2 dot a2 plus l by k b3 dot a2 minus h by h b1 dot a1 minus k by h b2 dot a1 minus l by h b3 dot a1. So wherever you see these indices are different, that will vanish, because we have ai bj is equal to delta of ij. So this will vanish, this will vanish, this will vanish, and this will vanish. So the two terms that will be remaining are this k by k b2 dot a2, and b2 dot a2 will be 1 because these indices are same. So that is 1 minus this also be 1, h by h b1 dot a1, b1 dot a1 is 1 and h by h is 1. So 1 minus 1, what you have finally is 0. So what you get here is this dot product of hkl and ab is 0. That means h of hkl is perpendicular to ab. So now we have took an edge of this triangle and showed that ab is perpendicular to hkl. By similar argument, you can also show that h of hkl is perpendicular to bc as well as ac. Now since to all these lines h of hkl is perpendicular, and these lines are in the plane of that are in that Miller plane, that h of hkl has to be perpendicular to this plane as well. So the sufficient statement would be to, if a vector hkl is perpendicular to any of the two non-parallel planes, non-parallel line on the same plane, then it is perpendicular to that plane as well. So that is why h of hkl is parallel to is perpendicular to this Miller plane. So that is the first statement that we have established. Now let us look at the second statement. So this is what we have established, h of hkl is perpendicular to hkl plane. Now let us look at the other statement, how this hkl is 1 by dhkl, where dhkl is your distance from this origin to for example, if you see this diagram, your dhkl will be from this origin to this, that will also be dhkl. From here to the next plane, if that will be also dhkl. So from origin to this particular plane, this first plane, if you can prove it is dhkl, then it is going to be the same for all other planes. So let us start with that. So let us take the unit vector along this hkl, h of hkl. So what do we do to get the unit vector? We just divide by its magnitude. And what is this vector? D of hkl is nothing but the component of OA along the line which is perpendicularly joining from O to this plane. I hope this point is clear. Like the projection of this OA along the line normal to this plane will give you your O, the shortest distance between O to this plane. Is that one clear? Like if you think a bit, it will become clear. So what we are doing here? What?
I have to go through it fully, then I can actually.
Yeah. Like please go through it. Like if you like have a bit of intuition, you will be able to figure it out. So what we are, so the claim is the distance from this origin to the plane is nothing but the projection of this OA vector along the line which is perpendicular to this plane. And just now we have seen that h of HKL is perpendicular to this plane, and the unit vector along that perpendicular line is h of HKL divided by HHKL. So this DHKL, so that is what it is. I mean, the statement what I made is the projection of A1 by H along the line which is perpendicular to the plane ABC. So you just have to take a dot product. It is just the mathematical form of the statement that I told. Now A1 by H dot, what is N? N is nothing but this H of HKL divided by magnitude of HKL. What is HKL? H of HKL, it is H B1 plus K B2 plus L B3. So this is the definition of H divided by its magnitude. So when you just evaluate that out, this A1, so now you know that A1 dot B1 is 1, but A1 dot B2 is 0 and A1 dot B3 is 0. So all you have is, so this term will cancel, this term will also cancel, this is A1 dot B3, that will cancel, this will cancel. The only thing that you will have with you is this H by H, also it will give out 1, A1 dot B1 is 1. So in this square bracket what you have is only 1, and there is 1 by magnitude of H of HKL. So what you have finally is 1 by magnitude of H of HKL. So on the left hand side you have DHKL, and on the right hand side you have 1 by H of HKL. So this basically means D of HKL is 1 by H of HKL, or take the reciprocal of that equation, you have H of HKL is nothing but 1 by DHKL. So these are the two lessons that we learn about the reciprocal space. So what are the things we got? Like we started with a crystal structure. That crystal structure is defined by some unit vectors. Corresponding to that unit vectors, we defined the reciprocal unit vectors. Now once we have that reciprocal unit vectors, we can define any general vector in that reciprocal space which we denote by H of HKL. And we saw that this H of HKL is perpendicular to the plane HKL, and the magnitude of H of HKL is nothing but 1 by the inverse distance between the these Miller planes. So that is what we have learnt till now. Now let us look at what will be the conditions for diffraction and how do we know about it. So when we send in certain so we know that this, what is this K? K is nothing but 2 pi by lambda, where lambda is the wavelength. Now so this is what we learned. H of HKL is perpendicular to this HKL plane, and HKL is defined by HB1 plus KB2 plus LB3, and the magnitude of that is 1 by DHKL. So let us look at in the real space what is happening. So let us say that some light is falling like that, some light or some waves is falling. That waves can be like, mostly it is X-rays, or it can be electron, so electron rays, electron beam, anything. So let us say that X-rays are falling like this, and it is getting getting refracted by this plane. So what these blue lines are denoting, these are the planes of the atomic planes. So along this, if you just, so this is one of the plane of the crystal, another atomic plane of the crystal, and this is the third atomic plane of the crystal, and the light is falling from top, and it is getting diffracted, and the angle of, so it is making an angle theta with the plane. Now this OA is this line. OA is the interplanar spacing, the space between the two planes. Now what we want to find out, that suppose if we have a detector here and we want to find if we will see a signal here or not. So what is the strategy to do that? The way to do that is to see when this beam 1 and beam 2 are interfering constructively with each other. To determine that condition of constructive interference, we need to know what is the extra path the beam 2 has taken with respect to the beam 1. So if you draw the perpendicular lines from here, from O to OB, which is perpendicular to AB, and OC perpendicular to AC, then the extra path that beam 2 has taken is BA plus AC. This is the extra length the beam 2 is taking. Okay, so this is the additional distance traveled by beam 2. Now, so it is the same diagram. So light is coming here and going away like this, and for beam 2 it is coming like this and going away like this. OA is the interplanar spacing, and this OB is the perpendicular perpendicular spacing between these two beams, and OC is the perpendicular spacing between these two beams, and OA is the interplanar spacing. If theta is the angle at which the light is making with the sample, or so this is your plane. Theta is the angle that the light is making with the plane of incidence. So this is the plane with the atomic plane. So if this is theta, and we are saying that we are making a 90 degree here. So if this is theta, then this angle is 90 minus theta, and if it is 90 minus theta, then this angle is theta. I hope this point is clear. Similarly, this point is also this angle is also theta. Okay, so now we have a right triangle here. AOB is a right triangle with right angle at B, and this is the hypotenuse, and these are the two sides. So the extra distance BA will nothing but d sine theta. So BA has a magnitude of d sine theta. I hope this point is clear. And similarly, AC will also have a magnitude of d sine theta, because this angle is theta now. So the additional distance that is travelled by beam 2 is BA, which is d sine theta, plus AC, which is again d sine theta. So d sine theta, we have 2d sine theta. So this is the additional path difference that beam 2 takes with respect to B1. Now if you want to put a detector here, we want these two beams to constructively interfere so that we get some beam. So if you want a constructive interference, what is the condition? The condition is that they have to interfere in a constructive way. So if this is one beam, the other beam also has to be along this, and the shift of this beam has to be an integral multiple of this lambda. So if you shift, so if this is your lambda, if you shift it by integral values, integral multiples of lambda, you will again have the same overlap. Like, I hope this point is clear at least. So that is why we want the path difference should be an integral multiple of lambda. Okay, so what we have here is the path difference, which is shown in the left hand side, 2d sine theta. It has to be 2d sine theta, it has to be equal to n of lambda, where n is an integer. So this condition is called the Bragg's law. D is the interplanar spacing. Here this D is the interplanar spacing. Sin theta is the angle which you can get experimentally. It is the angle at which you are incidenting your X-ray or some electromagnetic waves, and lambda is the wavelength of that incident wave. Now what we have here is n lambda equal to 2d sin theta. This is the Bragg's law, and this you have got in the real space. Now let us look at the same thing in reciprocal space. Okay, So before going to reciprocal space, like we'll see like what would be the condition for the light to actually interact with the the crystal points or the lattice points of the crystal. So let us think that there are two lattice points O and A. That means this distance OA, this can be obtained by some linear combination of the unit vectors a1, a2 and a3, and such that this p, q and r are the integers. That's what we mean. So what does this impose? When p, q and r are the integers, then the vector joining o to a, they has to be an integral multiple of, or the integral linear combination of the unit vectors, because like from the origin all the lattice points can be obtained by integral translations of these uh, unit vectors. Okay, so that is why when you take the difference of 2 points, let's say O and A, then what you will get is you will just get again an integral linear combination of a1, a2 and a3. Now what we want to do, we want to send in some light. So S1 is a light beam, S1 is a light beam and it is getting diffracted along this way. So S0 is the incident beam and S is the direction of the beam after some diffraction. So here also this is S0, another parallel beam in the same direction S0, and this is S. Now you see, if this is S0, so this dotted green lines, that is also S0. And from here, if you are taking this as S, so this O along this direction is S. If you go in the reverse direction, O along this is minus S. Okay. Now what we want to find? We want to find how this can interfere constructively. This beam which is deflected from O and the beam which is deflected from A. So let us find the path difference and then we will equate it to the integral multiple of lambda. Okay. So what is the path difference? Path difference is nothing but, so what we are doing, we are taking a perpendicular projection and this AB is the extra path. So if you draw a perpendicular line here to this beam, and whatever the extra path here you get is AC. So AB and or BA and AC is the extra path that the second beam is traveling. Now what we can do is this AB you can think of it as, now think of this parallelogram ABOD. Now AB is parallel to OD. Okay, along, and what is OD? OD is nothing but the component of OA along S0. I hope this point is clear. So AB is equal to OD and OD is the component of OA along S0. This point is clear, I hope. Or like you can like think for a while. Okay. You go back. Now similarly, this distance AC.
Just 1 minute. I'll be out for 20 minutes in between, like around 3 o'clock and 3:15. I have a call, company call, so I'll finish that and join back.
Excuse me, can you please say that again? I couldn't hear somehow.
No, I said that I'll be out, means I'll be out of the meeting for 15 minutes, 3 to 3:15, and then come back
Okay,
for the
sure.
problem solving.
Yeah, should I pause or something?
Yeah, if you can pause for only problem solving, we can start after 3:20. That will be good, sir. Because 20 minutes I'll go and come back.
Okay. or maybe I will continue. You can see from the recordings.
Okay, sir. Because problem solving we usually interact, so that's why I thought it's good
Yeah,
to
yeah.
understand.
Oh, we'll go on to the problem solving. Like this will be finished. I will just record this part, and
Okay,
so when you come back, we'll do the problem solving. Okay.
okay.
Yeah, I will just continue with this. When you just come back, we'll do the problem solving.
I'll be there at 3 o'clock. Only 3 o'clock I'll get out.
Only?
At 3 o'clock only I will leave. Yeah. 3 p.m. 3 p.m. only I will leave.
Oh, you are like leaving now or what?
No, sir. 3 p.m. 3 p.m. I will leave and come back by 3:20.
3 p.m.
Sorry. I'm sorry. Actually, I told you the wrong time. 8 p.m.
Okay,
8
okay,
p.m.
okay.
I will
Huh.
leave and 3:20 I'll come.
Okay, okay. Sure, sure. Yeah. You can leave anywhere like whenever you feel like. So I'll be continuing. You can when you join for the problem solving, I can discuss that again. Okay.
Okay, sir. Thank
Yeah,
you.
sure. Okay. So what we have here is like we're trying to understand this the path difference between the beams which is getting scattered by O and A. O and A are the real space lattice points. So we saw that OD, this OD is the component of OA along the S naught vector. Similarly, EO, EO is this, EO is the component of OA along minus S vector. So what is the total path difference? The total path difference is BA plus AC. So this BA plus AC, and we are taking the the parallel part OD plus EO, and OD is component of OA along S naught. So that is OA dot S naught, and EO is component of OA along minus S. So it is OA minus S vector. So if you take this OA vector common, you take the OA vector common, what you have is S naught minus S. And if you just take this minus sign out, you have minus S vector minus S naught. You just like inverting the sign after taking this out. Okay. So what you have now is the path difference is minus S vector minus S naught vector dot OA vector. So this OA vector is a lattice vector, and since it is a lattice vector, it can be represented as a linear combination of A1, A2 and A3, which are the real space unit vectors, and this PQR has to be integers. We still don't know what this S1 and S and S0 are, but like if this path difference has to be converted into a phase difference, so we just have to multiply 2 pi by lambda times this path difference. So it is nothing but 2 pi by lambda times this path difference, and this lambda, if you take it inside the bracket, what you have is minus of 2 pi S by lambda minus S0 by lambda dot OA. Now if you see the quantity in this bracket, it has to have a dimension of 1 by lambda, or the 1 by length, or the reciprocal of the length. So this is a vector in the reciprocal lattice space, and since it is a vector in the reciprocal lattice space, it can be written as a linear combination of the reciprocal unit vectors. So this S by lambda minus S naught by lambda can be written as H by B1 plus K by B2, so H B1 plus K B2 plus L B3. Where now this HKL can be any arbitrary values. They need not be just integers or just fractions. They can be any real values. Okay, we're just saying that this vector is right now in the reciprocal lattice space. So till now we have no restriction on HKL for now, and it need not be a valid reciprocal lattice point or lattice location. It can be anything, any vector, because HKL need not be an integer. Now what we require is that, let us just evaluate the path difference. So this s by lambda minus s naught by lambda, that we have replaced it as hb1 plus kb2 plus lb3, and here we have written this p a1 plus qa2 plus ra3. Remember that p, q and r are the integer values, they are the integers. Okay, now when you expand this dot product, and we know that ai bj, their dot product is delta ij, what we have is a b1 dot a1, that is 1, and the dot product of b1 with a2 and a3 are 0. So we'll have hp plus kq plus lr. So now what we require? We require that the phase difference has to be an integral multiple of 2 pi for the two beams, these two beams. If we want these two beams to constructively interfere, the beam which is uh, diffracted from A and the beam which is diffracted from O, if they want to constructively interfere, so now we are imposing the condition that they has to constructively interfere. So for that to happen, this quantity has to be an integral multiple of 2 pi. Now if this has to be an integral multiple of 2 pi for any arbitrary integers p, q and r, so what we need to have? We need to have hp plus kq plus lr. It should have to be an integer, and p, q, r are any integers. So if we are imposing that p, q and r are the integers and any arbitrary integer, and for all such values of all possibilities of such integers p, q and r, we need this quantity to be an integer, then we need to have h, k and l also to be integers. Without that it cannot happen. And once we have the condition that h, k and l are integers, we are sure that this hb1 plus kb2 plus lb3, they lie on a particular reciprocal lattice point. Now since it lies on a reciprocal lattice point, it is a valid reciprocal lattice vector. So this s by lambda minus s naught by lambda, it must be a valid reciprocal lattice vector. And so this tells you about what is the so this has the information about the source of the probe beam, and this tells you about the material and how they interact and what do we detect, that is given by this. This has to constructively interfere, and for constructive interference this has to come this has to become this has to be a valid reciprocal lattice vector. So now we understood that this has to be a reciprocal lattice vectors, and to get some diffraction pattern, like some constructive interference has to happen between O and A, and that happens when h, k, l are integers. Now let us take uh, another lattice vector OB, and so let us think of this O. It is some point in the reciprocal lattice space. It is some point in the reciprocal lattice space, and this s by s naught by lambda is this. If this is your s naught by lambda, and uh, let this AB be given by s by lambda. S by lambda is nothing but your s by lambda is nothing but your this vector. This is your s by lambda vector starting from here. So this is your another vector. Now what is this vector? S by lambda minus s naught by lambda. So this is s by lambda from here to a from a to b, this is s by lambda, and minus s naught by lambda is what? So this is s naught by lambda, and minus s naught by lambda is this. Minus s naught by lambda is this. Now, if you do the vector addition, minus s naught by lambda plus s by lambda, what you get is this OB. This is minus s naught by lambda plus s by lambda. So what we have here is this OB is a valid reciprocal lattice point where this h, k and l are integers. Now you see these points and this point O, this point B, they lie on a circle or a like circle when it looks so when we look in 2 dimension it looks like a circle, but when we look in the 3 dimension it will be a sphere, and that sphere would be containing so that sphere would be intersecting with certain number of points. Okay, and those points in the reciprocal lattice space which is those points in the reciprocal space which it is uh, which this sphere is touching, they will satisfy the condition that s minus lambda minus s naught by lambda is equal to hb1 plus kb2 plus lb3, where h, k and l are integers. Okay, and this particular sphere tells you that whatever the, so what it will tell you, it tells us that this it tells us the direction and the wavelength at which the diffraction can happen. So these are the possible uh, reciprocal lattice points which can participate in the diffraction. So this particular construct is called the Ewald sphere. So what it tells, the circle which touches, or circle or the sphere in 3D touching any of the points in the reciprocal lattice space. So whenever this circle or the sphere it will touch with a reciprocal lattice point, it will satisfy the condition of diffraction. So this is how we get the Ewald sphere. So now let us look at some of the examples. So till now the general idea is that we looked at a crystal. From that crystal we know what are the real space unit vectors. From that real space unit vectors like a1, a2 and a3, they are the unit vectors of the real space. From there we know how to define the reciprocal lattice vectors b1, b2 and b3. And once we have b1, b2, b3, now we can talk about different so once we have this b1, b2 and b3, we can construct an Ewald sphere and determine the properties like diffraction and so on. So that's the general idea. So now let us take some examples and determine what is the reciprocal lattice vectors of some of the simple systems. Like many material systems are in real material systems, they will have different crystal structures, but we'll look at 3 examples. One is simple cubic, one is face centered cubic, and one is body centered cubic. So let us just do that. So what we have here is we start with the example of a simple cubic structure. A simple cubic structure is nothing but a structure with the lattice points at the corners of a cube of side A. Corners of a cube of side A. Okay. So if you take this as origin, this point as origin, so this will be your ax cap. So a1, so if this you define as a1 vector, a1 vector is ax cap. So if this is x, this is y, and this is z. So this is a x cap, this is a y cap, and this is a z cap. A z cap. Your volume B is A1 dot A2 cross A3, and it is nothing but A x cap dot, you just put in these values, A x cap dot A y cap cross A z cap. So you take this scalar values A cube, like, so this A 1 2 3, they will come out, it is A cube, and you have x cap dot y cap cross z cap, which is x cap dot x cap, it is nothing but 1, and what you have here is that volume is equal to A cube. Now you got the volume, and now the definition of B1 is nothing but, B1 is A2 cross A3, A2 cross A3 divided by V. So A2 cross A3 is what? A2 cross A3 is A y cap cross A z cap. So A square by A cube is 1 by A x cap. So what you have is B1 is x cap by A. By similar calculation, what you will get is B2 is y cap by A, and B3 is z cap by A. So what you have in the reciprocal lattice is, you will still have, so what is this B1, B2 and B3? You see all of them has magnitude of 1 by A, and they are along the direction of x cap, y cap and z cap. So it is again a simple cubic structure, but with side 1 by A. So the reciprocal space of a simple cubic structure of lattice constant A is again a simple cubic structure with lattice constant 1 by A. Now let us look at what is your like, let us say that a crystal structure has a face centered cubic lattice point. So for a face centered cubic lattice, it looks like this. So just for the sake of explanation, so a face centered cubic is, so you have a cube, here, and you have a point here as well. So what we are going to say is, so if this is your x cap and this is your y cap, so this is A by 2, so if this is your A, this is A by 2 x cap and A by 2 y cap, oh sorry, z cap, this is z, and this is, yeah, okay. Now, so this is one of the face center, this is the other face center, this is the other face center. It is like, it is like the face of, if you just see this thing, so it is this face and this face from this corner, okay, and this is your x, this is your y, and this is your z. So this is like one of the, and your lattice points are here. This is your face centered cubic. From here, this is A by 2, so this distance is A. So this is A by 2 x cap plus z cap, this is A by 2. So these are the 3 points we are talking about here. I hope this point is clear. So this is one unit vector, this is one unit vector from here to here, and this is another unit vector. So this is one vector, one vector. So these are the three, the A1, A2 and A3. So once you have this, and when you put back, you do the same calculation, you find what is A2 cross A3, and then you do A1 dot A2 cross A3, you get V is equal to A cube by 4. And what you get here is this B1, B2 and B3, you will get, so what is this thing? So this thing is, suppose if you have a cube here, if you have a cube here, and you are starting from this origin, this is your x, this is your y, and this is your z. Now you do this thing, multiply this with 2 and divided everything by 2, by 2, 2, 2. Okay, now it is, you see, this is minus x cap by 2 is, you will just go to this, if this is your, this is your x cap, this is x cap, minus x cap by 2 will come here. Okay, and now you want to go y cap, along y cap plus y cap by 2. Okay, and z cap by 2 is this. So where you are reaching, you are reaching to the body center of your neighboring sphere, which is just minus, in the direction minus x to it. Okay, similarly if you do this b2, so it is plus x cap, but now minus y cap and plus z cap. So you are reaching to the body center of your neighboring sphere and neighboring cube, which is along the direction of minus y cap. Okay, I hope this point is getting clear. And then what is this b3? b3 is you are going plus x cap by 2. So from here, this is one vector, from here this is one vector, then the other vector is plus x cap by 2, plus y cap by 2, and minus z cap by 2. So you are at the neighboring body center of the neighboring cube, which is just which is along the direction minus z cap. So this is your another unit vector. Okay, so from the edge of a cube to the neighboring body centers, if you are going, so this is defining what? This is defining that it is a reciprocal reciprocal uh, so this structure is nothing but, this structure is nothing but a body center cubic structure, and this is in reciprocal space, and this is a reciprocal this is a body center cubic structure of lattice constant 2 by a. Okay, note that the dimension is 1 by length again. So a real space FCC lattice, if you go to the reciprocal lattice, it looks like a body centered cubic lattice. Okay, now let us look at what happens for a real space lattice. For a real space BCC lattice, for a real space BCC lattice, what you have is, for a real space body centered cubic lattice, it looks like this. So you can just now we have discussed like why this minus x cap plus y cap plus z cap. So what this means is, you just have to think of it as like this. This you can think of it as this, you can think of it as this, is equal to a minus x cap by 2 plus y cap by 2 plus z cap by 2. Again, what this means is, if you have a cube here and if you are starting with this, and here you have another cube, what you have with you is, you are going along x cap, this is y cap, and this is z cap. So minus x by 2 is here, minus x by 2 plus y by 2 plus z by 2. So you are reaching the body center of the neighboring cube, which is along the minus x direction. Okay. Similarly, you can and this is a side A. So this is a BCC structure of sides A. If you calculate the volume of the structure, you will get A cube by 3. The volume of this unit cell, it will come out to be A cube by 2. Okay. Now, if you do a reciprocal lattice, just the same calculation, what you will end up with these structures, and this notation, just like we had seen, it is like a reciprocal spacing. So this is a crystal structure of FCC lattice. So what we saw is, if you take the crystal structure of FCC lattice in reciprocal space, then it is a BCC lattice, and if you take the reciprocal lattice of the FCC structure, it is in BCC, and vice versa. So that's what we learned. And for simple cubic, it is again a simple cubic. Okay. And here also, so what would be the size of this lattice? So you have to do x by 2, y by 2. So this has a size of a by 2. So it is an FCC of size a by 2. Sorry, 2 by a. This is 2 by a, and so this is your reciprocal lattice. Okay. Now let us look at some of the questions. So what is the main difference between a real lattice and the reciprocal lattice? So both have units of length. So this statement is clearly wrong. Why wrong? Because the units of a real lattice, it will have a length unit of L, and in reciprocal lattice it will have unit L inverse. The reciprocal lattice has unit which is inverse of wavelength. So reciprocal lattice, so this statement is true because it is like inverse of wavelength. So lambda, it comes in the denominator. You have seen that this kind of uh, notation we had used in just some previous slide. So this statement is true. Okay. For some crystal structures, the representation in reciprocal lattice is different from that in real lattice. So what this means is, like for example, the representation in the, like for example, BCC structure, the representation of the BCC structure in reciprocal lattice is FCC structure. Okay. So it is clearly different. FCC structure is clearly different from, so FCC structure, if you take the reciprocal lattice, you get BCC structure. Okay. So this statement is correct. Now the fourth point, let us see. Reciprocal space is a representation of real space in a different framework. So this statement is also true because we are just representing. So this, if we know a1, a2 and a3, this represents our real space, and if we know this, we can easily get b1, b2 and b3. And if we know b1, b2 and b3, we can easily get a1, a2 and a3. So there is basically no difference between, so it is just a different representation. Okay. Now let us look at the next question. Yeah. So when correlating the real space with reciprocal space, what can be replaced at the question mark in the below given figure? So what we have is here, like, what can be replaced for this question mark? That is the question. So you see, so we want to find a replacement for this question mark. Okay. So what is this thing? So if you take a cross product of a1 and a2, so, and if you apply the right hand thumb rule here, like from a1, if you keep your fingers along a1 and swap it towards a2, then the direction of your right hand thumb will give you this. So so that would be the direction of, you see, a1 cross a2, a1 cross a2, this you will find in b3. b3 is nothing but a1 cross a2 divided by the volume. Okay, so that is going to be the direction of b3. Okay, so this is your correct answer. And why others are not? Because you see, b2, what is b2? b2 is nothing but, b2 will have, it is 1 by v a3 cross a1. a3 cross a1 is what? a3 cross a1 is a plane which is perpendicular, it will be along this direction, a3 cross a1, which is perpendicular to a1 as well as a3. And what is b2 cross a1? b2 cross a1 will be along a3, which is not true, and b1 cross b3 will be along a2, which is also not true. So this question mark, the axis from like it is along OD, so it has to be along a1 cross a2, which is nothing but your b3. So if a, b and c are the lattice vectors in the real space, and if n is the unit vector, and it is given by this hb1 plus kb2 plus lb3, then what will be the dot product of the unit vector? Yeah, see, so what it is saying? It is saying that if a, b, c are the lattice vectors in the real space, okay, and n is the unit vector given by this, so this is nothing but h of hkl divided by the magnitude of h of hkl. Okay, this is the unit vector which is perpendicular to this plane abc. Okay, unit vector perpendicular to abc. Then the dot product of, so this you are saying your n cap, dot product of n cap and a1 by h. What is a1 by h? a1 by h is nothing but this is your oa, is your a1 by h. So what you are basically planning is, what you are basically doing is taking the component of oa along n cap, so that will give you nothing but the distance from O to this plane ABC, and that distance is nothing but d of this h, k and l. So your correct answer is this dhkl. And what is this dhkl? That is nothing but your interplanar spacing. So these are the two correct options. Okay. So now let us assume ABC and B1, B2, B3 are the real and reciprocal lattice vector representations respectively. And if magnitude and directions of the reciprocal lattice are calculated by this, then what will be the volume of BCC and FCC structure in the, okay, in the representation of the reciprocal lattice space? So volume of BCC, this is given by A1 dot A2 cross A3, where your A1 is given by, so for BCC A1 is given by A by 2 minus x cap plus y cap plus z cap. Similarly, A2 is given by A by 2 x cap minus y cap plus z cap, and A3 is given by A by 2 x cap plus y cap minus z cap. Okay, now you just put all this formula, put all these values here in this, you will get a volume. Okay, and here we just had calculated that volume turns out to be, for BCC it turns out to be A cube by 3, and for FCC it turns out to be A cube by 4. So uh, it is, the correct answer is A cube by 2 and A cube by A cube by 4. So your correct answer is this. And for the volume of FCC, it will be just the same formula, A2 cross A3, but now A1 will be A by 2 x y cap plus z cap plus z cap, and A2 is A by 2 x cap plus z cap, and A3 will be A by 2 x cap plus y cap. Okay, so the diffraction condition in, so this is your correct answer. Okay, so the diffraction condition in real space and reciprocal space are given by, okay, in real space we saw that it is the Bragg's condition which gives you the, so 2d sine theta equal to n lambda. This is what we saw in the real space. And in the reciprocal space, what we saw, it is s by lambda minus s naught by lambda. It has to be an, this has to be a reciprocal lattice vector. So these are the two conditions. So or it is the Bragg's law, this is the Bragg's law, and this is the Edward sphere construction. It told us that whatever the so whenever this s naught by lambda and this s by lambda are in a sphere, if these 2 points corresponds to a sphere called Edward sphere, so this point is here, this, then they will so this satisfies the condition of diffraction. So this is your correct answer, Bragg's law and Ewald's sphere construction, or 2d sine theta equal to n lambda. This is your mathematical form of Bragg's law, and this is your mathematical form of the Ewald's sphere construction. Here h, k and l has to be integers, that has to be taken care of. And here why we cannot take this, why, because here this 2 pi factor is there, so this is uh, here you see there is a dimensional mismatch. This is a number while this is a dimension of L inverse, so this cannot be your answer, so your correct answer is only this and this. Okay, so now let us look at some of the other questions. So what causes directionality in a solid? So the directionality in a solid, that means the anisotropy, that anisotropy is caused by the crystal structure. The reciprocal space describes the interaction between dash in a greater detail than the real space. So it is the interaction between, so what we saw, it is the interaction between the waves. So waves is what, so the crystal structure is this, we had the crystal structure and we looked at how these waves, so one wave is coming like this, other wave is coming like this of lambda, and we saw it is the waves which is interacting with this crystal structure, right? So your correct answer is crystal structure and the waves. So the magnitude of a lattice vector HKL in lattice vector, so HKL in reciprocal space, we had just seen this HKL, it has d of HKL. So, and since it is talking about the magnitude, this like 1 by this d vector HKL, this is not the correct answer. This 001 and 1 by d001, so this talks only about a particular plane, whereas this talks about HKL plane. So your correct answer is 1 by d HKL. The dot product of two vectors in a real space being 0. So dot product of two vectors in real space is 0. That means this is a vector OA and OB and they are perpendicular to each other. That is why the dot product is 0. Signifies that the two vectors are perpendicular to each other. So which is true? So this is true. So because let's say OA dot OB is equal to 0, that means OA, the magnitude of that, OB, the magnitude of that, and cos theta is equal to 0, and this magnitude is non-zero, so that means cos theta is equal to 0. That means theta is equal to 90 degree. So according to Bragg's law, the total path difference 2d sin theta should be an integral multiple of this. So we just saw, so what we saw? So we saw that if this is our two crystal planes and light is coming like this and it is going like this, again it is coming like this, and we had drawn that interplanar spacing is d and this is theta, and so what we had is this distance, this is the extra distance and this is the extra distance. This distance has to be so this is d sin theta and this is also d sin theta. So total path difference 2d sin theta, it has to be an integral multiple of the wavelength, so that, so if it is an wavelength, so if it is coming like this, then the other one has to, for constructive interference, it has to shift by an integral multiple of this unit, which is nothing but your lambda. So it has to be wavelength. So this is your correct answer. So the equation S by lambda minus S naught by lambda in reciprocal space, it contains properties of all the waves which are dash from the lattice. So it contains the properties of all the waves which is diffracting from the lattice. So what we have here is s by lambda minus s naught by lambda. So this tells us about what is the wave coming into the lattice, and sorry, so this shouldn't be diffracting. So this has the information of what is coming into the lattice. This is s naught by lambda, let's say, and this is s by lambda. So minus s naught by lambda will be this minus s naught by lambda. So I'm again constructing that. This is minus s naught by lambda. I've just taken this as reverse, and this is s by lambda. So if you do a vector addition of these two, so this quantity is s by lambda minus s naught by lambda. Okay, and if this happens to fall on a sphere, then only it is a diffracting. So it has information about the arriving wave vectors and the leaving wave vectors, but only if this fall on the evolved sphere, then only we can say that it has the information about the diffraction, the properties of the waves which is diffracting from the lattice. A three-dimensional sphere in the reciprocal space is known as evolved sphere, and it corresponding to a single wavelength satisfy diffraction conditions wherever the surface of this sphere will touch the reciprocal lattice points. So why? Because in the last example also we saw that whenever if this is the evolved sphere, and if we are taking this to be as naught by lambda, and the s by lambda has to be on this sphere only. Unless it is on this sphere, it will not satisfy that diffraction condition. Okay, so it has to be on that surface of that sphere. A simple cubic lattice in real space, when compared with its representation in reciprocal space, is such that in real space, if you have a simple cubic lattice of side A, then in reciprocal space what you have? Reciprocal space, just now we saw that it is a cube of side 1 by A. So none of the angles are changed because it is a cube. All the angles are 90 degree. Here also it was a cube. All the angles are 90 degree. So it is no angles changed. The face-centered lattice in real space is represented by a body-centered lattice in reciprocal space. So this is true. Just now we had seen that when you take a real space-centered lattice and take the reciprocal lattice of that, you will end up with a BCC lattice. And if you start with a BCC lattice, take the reciprocal space, then what you have is an abscissa lattice.
Can you explain that once?
Which one?
This face-centered in real space versus this thing. Can you mathematically just quickly?
Yeah, sure. I'll do that. See, just hold on. What we have here is, okay, let us start with, I'll start afresh here. So what is your face-centered cubic lattice? Face-centered cubic lattice means you have, let us start with the defining the real space unit vectors, real space lattice vectors. This is your, if you have a, so we want to define A1, A2 and A3. Okay. If it is your real space lattice vector, then this is your X, let's say, along this direction is your y, and this is your z. Okay, so at each of this so how will you represent this particular atom? uh, let's say this is a. Okay, so this is a by 2 x cap and a by 2 z cap. Are you able to get that? So I am drawing 3 points on the 3 planes.
Yeah, half of the 3 plane. Okay.
Yeah, so if I write a by 2 y cap plus a by 2 z cap, are you satisfied with like this is one? Are you able to imagine this?
Just to
So
understand, X cap and Y cap will be like this. Okay.
see, so or I'm drawing another view of the planes. So let's say this is x, this is y, and this is z, and this is a, a. a. So this, okay. So this is a, this is a, this is a. So this is one face center, this is one face center, this is one face center. Okay, and we are starting from here. So these are the 4 points which I am drawing in. This is a different view. Are you convinced now? This is like a1 vector. So this is a3 vector. A3 vector is a by 2 x cap and a by 2 y cap. You end up with this. Is that fine? This
Yeah.
vector. Now if you like, what is a2 vector? A2 vector is a by 2 x cap and a by 2 z cap. So a by 2 x cap and a by 2 z cap. So this vector from here, this is your a2 vector. Are you getting?
Yes, sir. Yeah.
Yeah, and this one will be a by 2 y cap. So this is a by 2 distance along y cap and a by 2 distance along z cap. So this vector is your third vector. Three face centers from this. From one corner we are going to three face centers. These are your three, a1, a2 and a3. Are you able to follow?
Yes, sir. Yeah. Got it. Yeah.
Yeah. So now since you have these things, what you can do now is this. So this is a by 2 x cap, sorry, y cap plus z cap, y cap plus z cap. This is a by 2 x cap plus z cap, and this is a by 2 x cap plus y cap. Okay. Now what we are going to do, we are going to take the reciprocalities. So b1 equal to a1 dot, sorry, yeah, b1 is equal to just the definition that we had learned, a2 cross a3 divided by a1 dot a2 cross a3. This is what we want to find, right? So what you get here after you do that is, I'll just show you the expression. So this we started with our FCC lattice in real space. So what we want to find is b1. What we want to find is b1. So a2 cross a3 divided by a1 dot a2 cross a3. So when you do this a2 cross a3, I hope you know like this cross product. So you find the cross product a2 cross a3 and then do the dot product with a1. You will end up with a cube by 4. That is your v, the denominator part. Okay, and A2 cross A3 you have found out, which is this. A2 cross A3 is this. If you divide that with A cube by 4, you will end up with this kind of expression. B1 is equal to 2 by A minus x cap by 2 plus y cap by 2 plus z cap by 2. You understood, right? So this you get after that mathematics that you do. So like let me explain you what this particular uh, thing means. Is you do this, just I am multiplying and dividing by 2. So what is happening is, let us start with a cube. So this is the reciprocal lattice space of so of the crystal structure which was abscissa in real space, right? So we started with a cube, a corner of a cube, and what we are going to do is, you see, let us try to understand this. The first one, B1. B1 is you are going, so let's say this is the side, you are going minus x cap by 2, so this is your x and this is your y and this is your z. Okay, you are going minus, this is your minus x cap, this is minus x cap by 2, then you are going y cap by 2, the half of this length, and z cap by 2. Okay, so you, this cube is like 1 by 8th of this bigger cube. You are able to see that, right? And here you have a point, and are you able to see that?
Yeah. Yes,
Yeah.
sir.
And the side of that cube, so this is what, minus x cap by 2 plus y cap by 2 plus z cap by 2, that is what it is. It is the body center of the cube which is along the minus x cap direction of the, so of this adjacent cube. Is that okay?
Yes, sir.
Yeah, this is the body center of this cube. So and what is the side of this cube? It is 2 by a. But this factor is not that important. What is important to see is that, so this minus x cap by 2 plus y cap by 2 plus z cap by 2 is the body center of the cube which is in the minus x direction of this original cube. The second one, this one is the body center of the cube which is along the minus y. So you imagine a cube which is along this direction, which is like coming out of the screen, and it is placed adjacent to this. That is your minus y direction, right? And imagine the body center of that. So I hope you are able to imagine. So this point is coming out of the screen, and that is your minus y cap by 2 plus x cap by 2 plus z cap by 2. So this is the body center of the another adjacent screen, and this one is x cap by 2, y cap by 2, and minus z cap by 2. That is the body center of the one which is below that cube. So for this particular corner, you have three cubes adjacent to it, right? And this 3 denotes the body center of those three cubes. So that is why it is a BCC structure. When you do the mathematics, it will be like more clear. So that's what it is. Like, I hope you understood. It will take like a bit of thinking, but you can do that.
Okay, sir. Yeah.
Yeah. So this statement is true. Like, if you take FCC lattice and do the mathematics and find out what is the reciprocal space, you will find that it is a BCC. And when you start with a BCC in real space, you will end up with FCC in reciprocal space. Okay. If wide radiation, meaning a range of wavelengths between a lower wavelength and a higher wavelength, is used to probe a crystal, this is represented entirely in the Ewald sphere notation by uh, okay. So Ewald sphere, what is the condition for the Ewald sphere? it was s by lambda minus s naught by lambda is equal to h b1 plus k b2 plus l b3, where h, k and l are integers. This happens when this is for a single wavelength. You have a single sphere in the reciprocal lattice, and whenever your reciprocal lattice points coincide with this, you have a condition for the diffraction. Now what you have a range of wavelength between a lower wavelength and a higher wavelength. So now since you have a range of wavelength, so it will cover more area in the evolved, like it will cover a volume. So if it corresponds to a let's say this s by lambda 1, and this corresponds to s by lambda 2. So lambda 1 is in denominator, so the shorter wavelength will correspond to uh, this long vector. Okay, so the this is represented entirely in the evolved sphere notation by two spheres, one with each radius one each with radius corresponding to lower wavelength and the higher wavelength. Okay, so it is saying that it is about the two spheres, but it is saying we have a range of wavelengths, so we should have a continuous series of wavelengths with radii ranging from uh, the higher wavelength to that of lower wavelength. Actually, it is continuous since we have a continuous range of the wavelengths, since it is a white light, our evolved sphere notation, uh, it will be a kind of cell from this to this. So your correct answer has to be this, the fourth one. Okay, this is not, it cannot be a single sphere. So when it is a single sphere, it is just a single if it is a single sphere, then it is just one particular wavelength of probe. But when you have a range of probe, you need to have that evolved sphere like a cell. So yeah, these are all about it. And yeah, so that's all for today. You have some other questions?
Can you go to the 1 and 2, sir? First two questions. Just, I didn't see it. What kinds of reaction is solid, crystal structure, reciprocity, is and interaction between.
Yeah, this you can understand, right? Why the directionality
First,
in the solid is caused by
that
the
is fine. Yeah,
anisotropy.
yeah, that is fine. Yeah.
Hmm.
Second one, there's interaction between crystal structure and waves. Is it okay?
Yeah, so why? Because
Okay.
like when we saw the interaction when we put in some light, we saw that it was scattering off by these crystal planes. It is because of this structure that this scattering happened, and these are the waves. And it is 2d sine theta. 2d sine theta is this d is the interplanar spacing. This tells you about the crystal structure. Okay, this interplanar spacing is equal to n lambda. This is about your waves. So it is about the crystal structure and waves interaction.
Yeah.
Yeah.
Sir, when you talk about the reciprocal space and the real lattice space,
Yeah.
real lattice and reciprocal lattice. So basically, both are having units of length, right?
No. Uh, the reciprocal lattice have units of 1 by length.
One by length. Okay.
Is it not? Because like in reciprocal space, if you just see, that's what we had discussed here. you see what is b1. B1 will be like, it is, you see, it is escaped by a.
Yeah,
It, a has the unit of length,
length, correct.
so b1 has the unit of 1 by l, 1 by length.
Okay,
Yeah.
okay. So can we say that reciprocal lattice has unit which is inverse of wavelength,
Inverse of wavelength, that is true. Inverse of
and
wavelength, what is
reciprocal
the
space
length?
is
uh, Inverse of wavelength means what? Inverse of length, so it is same,
wavelength.
it is true.
Yeah.
Yeah.
And what about the statement? What we can say, like reciprocal space is a representation of real space in a difference framework. We can say that, right?
Yeah, that is true. Why? Because given the reciprocal lattice vectors, you can find this. I think we just discussed somewhere. Yeah. So what it means is that given this a1, a2, and a3, you can find what is b1, b2, and b3. And given b1, b2, and b3, you can find what is a1, a2, and a3. So we can say that it is a representation of real space in a different framework. That is true.
Okay. So in the second problem, this question answers I didn't see, sir. When did you do this?
Oh yes, yes, this has been done.
Yeah,
Like,
okay. I missed this portion, I think.
yeah,
Okay. Can you explain this second question, sir? How did you solve
yeah,
it?
sure. Like when correlating the real space with the reciprocal space, what can be replaced with the question mark? So you understood the question, right? At least. So the
Yes.
question mark is shown in this green dot.
Yeah.
User pointer. This one is
I can
replaced.
see that. I can see that. Yeah.
Yeah.
It's like
So
y-axis. Yeah.
you have to find what is this vector. Okay. So you see this vector is perpendicular to a2.
So it's a right angle triangle. It's a right angle triangle. You take it like a right angle triangle.
Yeah, but the point to note here is that this direction is perpendicular to the parallelogram A1, this OACB, right? It is
Yes.
perpendicular to this. So if you take a cross product of A1 and A2, it will come along this direction,
Yes.
right? And it is the B3 vector which is along the direction of A1 cross A2.
Correct. Yeah.
So it is
Yes.
B3.
Okay. So yeah, got it. So,
Yeah.
if it is a triclinic structure, um, like A1, A2, A3 will have a particular angle, right, sir?
A1, yeah, yeah, it will have a particular angle, but so what's the problem in that? So
No, there is, yeah.
we want to find
Yeah,
about,
this I understood, sir. This question I understood.
yeah,
Yes, sir. Yeah, got it. Yeah. Go to the next. Yeah, here, sir. Yeah, this one.
yeah,
N cap is equal to HKL by HKL. This vectors, real space. DHKL and okay, unit vector 1 by I need little help on this, sir. Interplanar spacing and DHKL. Why do you say interplanar spacing?
interplanets. Oh yeah, this we had just discussed in the main thing where we have just a minute.
Chepo.
Yeah, uh, if you remember this particular slide, here we had denoted that this the projection of this. So you, I hope you understood what is. So first thing we had established that HKL is perpendicular to this plane, right? ABC.
Yes.
Okay. Now the second point is, if you take the projection of OA along the unit vector which is perpendicular to ABC, then you will get the interplanar spacing. So this distance from here to this particular plane is same as from here to this particular plane is same as from here to this particular, so there would be a plane here, then there would be a plane here which is at like equidistance. Like think of
Yeah,
this.
got it, sir.
Yeah,
Yeah, yeah,
yeah, so that is the reason.
yeah. In a triclinic structure, sir, A1 is not equal to A2, but equal to A3.
No, 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 in a triclinic
And
structure a1 a2 a3 need not be same, and the angles. So what is a triclinic structure, let me just tell you. So a triclinic structure is this, where this a1 need not be equal to a2, need not be equal to a3, and the angle
all
between
three.
these two, this and this, these three also need not be same. Like a1 need not be equal to a2, need not be equal to a3, and the angle between this need not be equal to this, need not
Need
be,
not be or need not be or cannot be.
need not be.
Okay,
Okay,
not
and if
necessarily.
they are equal, then there are different nomenclature. Like if alpha is equal to beta, then I think it is like some uh, like you will get into some other categories. But
Different structure. Okay.
usually, uh, if they are not same, then we say that it is triclinic.
Okay, sir. So when we say h by hkl, modulus of hkl,
Hmm.
then that means like the model like hkl is nothing but the vector hkl is nothing but the real space, and the modulus of hkl is in the other space. Is it right? You
I'm not
actually
getting.
had that this one. Yeah, this question n cap.
N
So
cap
the
is just a
hkl.
unit
Oh,
vector. It has
yeah.
no
Can
dimension.
you? Yeah, when you say HKL, the top one,
Yeah,
the numerator,
yeah,
and the bottom denominator,
yeah.
how do you say that? The numerator is nothing but reciprocal real space.
No, we are not saying about that numerator is real space. We are saying that n cap is a unit vector which is along the direction of this HKL. It has no
Okay,
units.
okay. So what kind of a lattice vector is that HKL?
It is see HKL. We are not saying that HKL is a lattice vector.
Okay, it's
H,
not a real lattice vector or a
HKL
because
is
it's a
just a
vector, right?
vector in the reciprocal lattice space.
It's a reciprocal lattice space, right? Okay.
Yeah.
So when we say HKL divided by modulus of HKL, it is in real space or in reciprocal space?
So like it need not be in any space. It is a, you can think of it as a vector. A vector can be in any, so it needs to have a direction, no units.
Okay.
So here we are talking about the direction, not the units. So when you take this, so what we are saying is that the statement is that
See,
this
in
direction
case when we say n cap is in real space,
n
can
cap.
we say if is in real space, the vector unit vector is in real space? Can
Okay.
we say HKL is in reciprocal space, and the small HKL we call it, right? The small HKL, or you can Miller indices. Miller indices is in the real space.
Miller indices in the real space. No,
So
see
because
this H
DHK,
of HKL, HKL is what? It is, it is a vector in the reciprocal lattice space.
correct. Okay.
Of,
What about the bottom one in the
yeah, just hold
modulus
on.
of HKL?
Yeah. Now you see what is this thing. It is the magnitude of this. So and the units
Yes.
of this, let's say this b1, b2, and b3 are let's say perpendicular to each other and all. So what you have here is just a unit vector which is along this direction. See, irrespective of the units, you can draw it as a vector, no, in any plane, in any space,
Yeah.
be it real space or what, lattice or reciprocal space. You
It's a
can,
plane, right? HKL is a plane.
HKL is a plane
That's in a real space.
that is in a real space, and edge of HKL is perpendicular to the direction of HKL is perpendicular to this plane ABC. See, the vector can be drawn in
Okay.
any space, irrespective of the magnitude
Okay.
or the units.
So when we say h by hkl, that should be in reciprocal space only then, because hkl is in reciprocal space. Then h by hkl also is in reciprocal space, correct?
Yeah, it is in reciprocal space. No, see, when we say that a particular vector is in a reciprocal space or real space, we look at the units. If the units is 1 by length, then it is in reciprocal space. If the unit is in length, then we say that it is in real space. If it is unitless, then it is just a vector. It is showing a direction. That direction can be in any space. Like, are you able to understand like this? Uh,
Yes, yes, got it, sir.
like, for example, when we say 5 meters towards north, here we are specifying a distance towards north, okay, or uh, but when we say north, then it is just a direction. It need not have a unit, it is just showing a direction. Similarly,
Yeah.
encap is just a direction, we are not specifying any unit.
So if we say, like, for example, one element or one metal is in FCC in the real space, can we
Okay.
say it is in BCC in the reciprocal space? Because that's
Yeah,
what we defined, right?
yeah,
So,
that's what it is, like, yeah, that is true.
so if it is BCC in real space, it will be FCC in the reciprocal space.
Yeah, that is true.
Opposite.
Yeah,
Oh, that is also true.
yeah.
Ah, okay, interesting. Okay. So diffraction condition is the real space and reciprocal space. Basically, real space is given by the Bragg's law, 2d sine theta equal to n lambda,
Yeah, yeah.
and reciprocal space.
See, in real space, 2D sine theta is the Bragg's law, and evolved sphere construction is the reciprocal space construction that we saw.
The previous question also, I need your help, sir. I just want to understand that question also. How did you solve that? The previous, no, that question, the question which you just showed. The next one. Yes, this one. How did you solve this? The fourth one.
Fourth one, yeah. So you just have to find the volume of BCC and FCC crystal structure representation. So how did you find? How do you find the volume of? So it is just A1 dot. Uh, okay, maybe. What will be the volume of BCC and FCC crystal structure representation in the reciprocal space? Yeah, you just have to find the volume of BCC and FCC. How do you find that?
Okay.
It is just A1 dot A2 cross A3, and you, like, we have seen what is A1, A2, and A3. It is
A1,
just,
A2, yeah, yeah, yeah,
yeah.
yeah.
You just have to put the formula, get the answer. That's what we have discussed.
So for A, we have not got the value, right, sir, here.
A.
So,
We
so
will
you're
have the
using the
unit.
A value as BCC.
A value as BCC is given here, like I have written here, no? This is A1 in BCC, A2 in BCC, A3. Like A1, A2, and A3 are
Yeah,
here,
correct.
and you
Yeah.
can,
Now, what I'm asking is the A value, lattice parameter itself,
yeah.
you're using the value of A itself from the BCC, basically, which is like root uh, A is what is the value? A by
We don't have
how
to
do you
put the value, no, we have to show in terms of A. Here like A cube is there. If you put some value,
A
then
cube by 2 and A cube by 4. Okay.
yeah. If you
But
just
4,
put,
1 by,
uh,
yeah. Like when you multiply this, we will be able to see it. That's what you're saying.
yeah, if you just put all these things here, you will see.
Oh, correct. Sixth question, sir. Question number 6.
Yeah. There is no sixth question, I think. This question you mean?
Oh, no, no, not this. This is all. Okay. Next question was one which we discussed already. Okay.
Yeah, yeah.
Okay, sir. I think, yeah. For the last class, sir, I need your link.
Yeah, yeah, okay, that I will send you. Yeah. This part is clear, right?
To an extent, yes.
Yeah, maybe if you
I'll go through
go
it.
back and revise,
Go through
then
it.
it will be
Yeah,
more clear. Okay.
I'll do that, sir. Yeah.
Okay. Thank you so much.